Welcome to CS352. This is week 3, lecture number 1. That means it is Tuesday. And as usual, we'll begin with administrative issues. So let's see, homework 1 is due tonight. Any questions about homework 1? Okay, well, I'll show you homework 2 and give you an opportunity to ask questions about that. Normally I wait to discuss the next homework until after the other homework has already been submitted, but homework 2 is a little bit longer. So let's jump ahead and look at homework 2. So I'll need to share the screen here. And apparently I did not bring up homework 2 yet, so I'll need to get that. So homework 2 will be due in a week and a half. I posted it 5 days ago. So in the hopes that some of you guys would, or all of you guys, would get started on it before now, but I realize probably a lot of you have not. Anyway, there's quite a few exercises. Typically the exercises don't take a lot of time. These exercises are relatively short, but some of them will require some time and thinking. So I'll give you an opportunity to ask questions about the exercises. This homework is all about recursion. Who is that?
That was me, Mel.
Okay, go ahead, Mel.
For number 2, I did it and I ran it and I don't understand why it gave me the output that it did.
Aha. Okay. So
I sat there for like 10 minutes.
Were you thinking or
just
sitting?
Yes, I was thinking. I like traced it. Yeah, I traced it like by hand.
And good.
I just don't. There's a certain aspect of it that I don't understand.
Well, you're doing the right thing. You're supposed to think and trace by hand. That's all you got. Yeah. So you ran it and you got the. Let's see. And so you're pretty comfortable. You and Jessica, you're pretty comfortable that you entered the code correctly and you ran it.
Yes.
And it gave you the output. Okay.
Yeah.
Good. And so then when you traced it by hand, you didn't come up with what the output showed you.
No.
Okay. Well,
obviously that's wrong. And I ran it in in 2 different compilers, so I know it's like behaving.
Okay. Now we might get to the point where I say, okay, let's talk about this one-on-one because I don't want to give too much help. But we're not there yet. We're not there yet. Now you notice number 3. I assume you and Jessica both looked at number 3 already?
Yeah.
Because number 3 gives you output that is more normal if you work at NASA. And I did, by the way, for one summer. Yay. That's so cool. Then the countdown would be like this, 10 down to 1, and then you say blast off. So I don't think it'll be giving away the farm here if I ask, was your output for number 2 different from this?
Yes.
Jessica, yes. Okay, good. That
yes.
is to be expected. Okay. Well, I guess let's begin answering your question with just a verbal trace with no writing. So main passes in the value 10, which is to be expected. I mean, we want the countdown to start at 10. Okay. So you pass in the 10. So is 10 greater than or equal to 1? Yes, it is. And so then you call countdown recursively, and you're going to be passing in a 9. I think you guys get that. Everybody gets that, right? You pass in a 9. So you're not printing out the value initially. No, you call this recursively, and you pass in a 9. We're not paying attention to else. We just pass in the 9. So then you pass in the 9 there, and is 9 greater than or equal to 1? Yes. So then you call this recursively, and that means you're passing in what value, Mel?
Are we at 8 now?
Yeah, you're passing in 8. Jessica, is that what you did? Yeah, okay, good.
Yes.
So far, so good. So you just pass in the 8. And let's just assume that you traced it either verbally, like we're doing it, or with a piece of paper. You could have a variable called n. And okay, so it would go from 10 to 9 to 8, and then all the way down to well, 1 is not anything special. If you have 1, that's still true. And so then you pass in a 0, right? So you got that far?
Oh,
Okay.
I think I see now.
Oh, okay. Well, you don't need to talk anymore then.
Okay.
Because I don't want to give a whole lot more help.
I think
But,
it had.
oh,
I had
I don't know. Are you sure you're going to talk?
no,
when
it's
I
not
get here?
incriminating. It's not incriminating, I
Okay,
promise.
go ahead. Go ahead.
It just in general has to do with the way that I was thinking about the recursive call and if it where it is executed.
Right, right. Yeah. Okay. So Jessica, so you got down to n equals 1. That's still true. And so then you have n minus 1 is 0, right? So you call countdown. So you pass in a 0. We have not traced this print statement at all yet. So I just said, okay, you pass in a 0. And then at that point, I don't know if I want to go any further. Did you do the same thing, Jessica, that I just described?
Yes.
Well, if you did, and this is a 0, you should be then printing something which matches your program's output, but it doesn't.
Mm-hmm.
Oh, man. Okay, let's talk after class.
Okay.
And I will be very specific after class. So yeah, we'll get to the bottom of it. Don't worry. But I don't want to spoil the fun for everybody else.
Is this
Go ahead.
Is this related to, I think, is it called like head recursion or something? There's 2 types of recursion. There's like a head one and then there's like a tail one.
Yeah, but you don't have to know those terms in order to do the trace. There's nothing special about knowing those terms. Tail recursion, and we will talk. Tail recursion is, yeah, you should know the term tail recursion because that does have a special quality, which we'll talk about it in about an hour. Head recursion, it doesn't have a special quality other than it doesn't have a special quality that allows you to replace it with loops. So that's not going to help you get the answer, just knowing those terms. You just have to trace it. And so, Ryan, have you started on it and you got the wrong answer and that's why you're asking, or are you just thinking?
I got the right answer. So
Okay.
just wondering.
Okay. Yeah. Okay, so that's number 2, and then number 3 asks you to change something in the code so that you get this more standard output for a countdown. Feel free to stop me. I'm just going to skim through the exercises. And number 4, I give you some code, and then I ask you to, basically this is a trace also, except I'm telling you to tell me the output. Okay, so to get the output, once again, you could plug it into Eclipse and run the program, or IntelliJ, which I think I like better now, Mel.
Oh my gosh, I converted you.
A big grin there from Mel.
Wow. Yeah, that is a big grin.
I don't know. I don't know if.
Well, because you're stubborn. I feel like you're kind of stubborn. So with your ways, like,
what?
I feel like you are very particular in what you like. So I feel very.
I'm very particular about elegance.
Yeah, so I feel like it's kind of a big deal to change your opinion on something. So I feel
elegance is
honored.
one particular thing. I changed. Okay, raising my kids. I'm very much okay with talking to my kids and getting their opinions and then changing the plans.
No, I know. I'm just saying, I feel like you're very, I don't know. Yeah, with your elegance, you're just very...
Elegance, I want to be elegant.
I know. And I feel like with IDEs, that's a big thing. So, no. Okay.
I've changed a ton of IDEs over the years.
Okay. Well,
and I'm learning Spring, and I'm going to change jobs.
Oh, wow.
Yeah. This is my last year at Park.
Oh.
Yeah, and that's why I'm learning Spring.
John, why
Oh,
are
who's
you
that?
leaving? It's Azora.
Oh, Zoda. Let me see. I better. Okay. Darn it. Okay, good. Now I've got the gallery view. Let's see. Speaker view, gallery view. I always have to do this after I start on my second computer. Well, Zoda or anybody, we can talk after class about that. That's not really appropriate for lecture.
Okay.
But yeah, so let's move on. Exercise 4, yeah, as I was saying, tracing it. And any questions on that? Run the program so that you know your output is correct. But you do need to be able to trace it by hand because for the exam and in the real world, you just need to understand how things work. Number 5, you're going to have to insert some code right here. And the whole point of this method is that it reverses the passed in. That's actually not passed in the normal fashion. We've got this scanner object called scan. And scan has a string embedded inside it. As I say up here in this description, you can, well, normally you're going to be using a scanner object for input from the keyboard. But as an alternative, you can use the scanner object to do input from a string. And normally with a string, you're not going to use a scanner object. You just use the string methods that you're used to, right? Substring or length and all those string methods that you've known and loved for years. But as an alternative, maybe you want to process or parse the string in a manner similar to how you read in from the keyboard. So that's what we're doing here, okay? We're going to be using the scanner object so we can read from the string using has next. Well, that's a method that you can use with keyboard input. You can also use it for string input. It allows you to loop through the string or loop through the keyboard input to find the next thing that you're looking for. And so you could use next int, next double, next float, next, all those methods that you've used with keyboard input you can use for the string. Anyway, we're going to use has next to determine if there's anything left in the string to read in. Now all that is just background information. The goal is to figure out code that goes here so that this reverse method works. So if you pass in the we are many string as a scanner object, this reverse method, get reverse method, is supposed to return this string such that the words are in reversed order. So it will return many are we, okay? And so using recursion, you can get a nice, elegant implementation just with a little bit of code right there. Okay, that's the goal. Any questions on that? I'm spending more time on these exercises because they're non-trivial. Okay, and then number 6. Okay, so number 6 asks you to modify this code so that you're using tail recursion. And that'll make more sense later on when we talk about tail recursion. So unless you have questions, I'll just skip over that for now. Okay, and then number 7, it's another tail recursion question. In lecture, we talked about the GCD method, greatest common divisor method. And with that code, we had tail recursion. And so I want you to convert that code by replacing the recursion with an iterative solution. Iterative means looping. Okay, and we'll talk about how to do that at the end of today's lecture. So those are the exercises. No more questions on those? Okay, and the project. The project is not very long, but it uses recursion So I would assume that some of you guys will be tripped up. I hope not. Hope it's easy for everyone. But part of this project is just figuring out the book's program. We've got a required textbook, right? I'm not sure how many of you guys are reading the book. I mean, you should read the book. It's got a lot of information. Now, it's true that I cover almost everything you need to know for this class in my lecture slides. But sometimes for the homework, I require you to dig into the book and learn a little bit more. So part of this problem is just reading the program, the T-square program in the book. It uses recursion. It's a little bit tricky, but read through it, try to figure it out, and then modify it a little bit. You don't have to do a lot of modifications. There's not a whole lot of code here. You just need to follow the instructions. So the book's T-square program generates this fractal picture. Well, it generates a fractal picture. And the fractal picture that it generates has two colors. And so the only thing you got to do with this project is modify that program so it generates basically the same fractal picture, except there's three colors. And so the three colors I chose are white and canary and wine. Why did I choose canary and wine?
Parks colors.
Parks colors, yay. Okay, everybody burst out into the park fight song. Does anybody know the park fight song?
I didn't even know we had one.
Oh, yeah. Big time. You know, you must not go to many football games.
We don't have football.
Oh, that's right. We don't have football. Oh, yeah. Okay. Oh, well. Yeah, we've got a fight song. And I don't know the lyrics, but yeah, at graduation, I've got to sing the.
I have a question on this project.
Good,
section.
go for it.
Okay, so I have two questions. First of all, is the resulting fractal image supposed to look exactly like that pattern, just different colors?
Yeah.
Okay. Secondly, the biggest problem I'm having is like where to implement the conditional / the switch statement. Should that be done inside of the actual like draw square method?
Yeah.
Okay.
Well, hold on.
Okay.
When I say that, I want to be sure.
I was thinking of putting it like in the else.
Yeah, it's in the draw squares method.
Okay, and was I correct to be putting it inside the else?
Well, there's different ways to do it, I'm sure. I don't put it in the else. But then again, I don't even have an if else. I mean, I modified that method.
Oh.
I streamlined the method a little bit. I thought the if was kind of dumb.
Okay.
It doesn't do much. It's silly.
No,
I
mean you can.
That.
Oh, I know. I see what you did. I see what you modified with the base case. Okay. So I guess I have an idea of what it needs to do in terms of like with the if else. Like it needs to obviously alternate between the every third or whatever.
Right. Toggles between the three of them. Yep.
Right, but I guess I'm having a hard time thinking about what would be the condition that alternates between the three. Because would it alternate between? Because there are 4 calls, right? When it recursively paints the squares in the corners, is that what it's supposed to be alternating between?
No.
No. Oh, okay. So maybe that's what I was having issues with. Just after every third, then, or after every.
Every time that method gets called, it'll use a new color.
Uh-huh. Okay.
So in that method, you need to toggle to the next color. Now that's the fun of the project is how do you do that? It doesn't require a whole lot of code, but it requires a little bit of thinking. And I'll be happy to discuss that in more detail, but one-on-one. We're getting a little
okay. Sorry. Go ahead.
No, that's good. You guys can always ask granular questions, and I might sometimes push that off to a one-on-one discussion. It could be in Zoom or just after class.
Cool.
Okay. Any other questions on that? As it says in my description up here, the style of the author's code is pretty good. but don't get lulled into thinking that it's good enough. Okay, the indentation is sometimes a little bit off. And you know me, I'm super picky and I never change my mind about anything. Kidding, Mel. But
Yeah.
I am picky about style, and I do want you to follow the style guidelines, and so you'll have to make a few changes to the author's code.
Does
To style.
does Java not have, because Python has PEP, like PEP 8 as its like style, like official styling guide. Does Java not have that, or do we just just Google just like have their own docs and styling?
I don't know what PEP 8 is. PEP 8, PEP 8.
Yep.
No, I've only used Python a little bit.
PEP 8
so
is it's literally, it's like by, I think it stands for something.
That's okay.
Okay.
That's okay. I believe you. I certainly believe you. Yeah, Google Docs. I'm sorry. Google has lots of style guidelines, and I follow Oracle's. We had that discussion offline about Oracle and Google. So I follow Oracle almost to the T. Anyway, any other questions about the homework? Okay, but first, homework 1 is due tonight, 11:59 p.m. So get that one done first, of course. Right? Okay. If there are no, oh, and we're doing the exams with ProctorU. I sent you an email. Well, I guess we voted on that, so yeah. Sign up for ProctorU if you haven't already done so. Whew. Okay, let me jump over to the slides. So we left off on slide number 23, I believe. Well, 22. I skimmed through the slides pretty quickly that described the algorithm for finding the largest number from a list. And you're supposed to do this on your own and compare your answer to this. I wasn't planning on doing any more with this. It's practice. Okay, the concepts aren't new. It's just another practice problem. But feel free to ask questions about it now that you've had more time to do it on your own, right? Everyone? Anyway, any questions? No? Okay. Then moving on. So when should you use recursion? By the way, recursion does not provide unique functionality. You can always replace a recursive algorithm with a looping algorithm or an iterative algorithm, it's more formally called. You don't ever have to use recursion. So why bother? Okay, I guess that's a rhetorical question there in that I've got the answers down below. So, I wonder why I said that. Okay, I'm introing it. Sometimes the recursive solution is more straightforward than a looping solution. Yeah, more specifically, use recursion if the problem has a natural recursive solution. So for example, with math-oriented problems, sometimes the definition is recursive in nature. And we already looked at the definition of factorial, the mathematical definition of factorial. And then we implemented a recursive solution using that mathematical definition. Likewise with greatest common divisor. So sometimes you'll have a math-oriented problem that's recursive in nature. So feel free to use a recursive programmatic solution. Also use recursion for some games, like the Towers of Hanoi game. That's the classic recursive game implemented with a programming language because the solution is so elegant with recursion. And if you don't use recursion, the solution is inelegant. It's ugly. Using arrays and loops, and yeah, it's messy. So classic, use recursion for Towers of Hanoi. Chess, I've never looked at the code for a chess program, but just thinking about it, yeah, you could implement a chess program recursively. Does anyone play chess online? No? Okay. Yeah, I'd invested 2 months of my life over the pandemic. I thought, okay, I'll be a world chess master after 2 months. No, didn't become a world chess master. Oh well. And then I didn't learn how to play the guitar either. That was my next thing. Oh well, I picked out a guitar, didn't buy it. Okay, so for chess, yeah, with the chess programs, you're going to analyze moves for the player. And the way you can do that is you pick out one move, and then based on that one move, you analyze what happens if subsequent moves occur. And for each of those subsequent moves, you analyze, okay, what happens based on those first two moves? What happens if you do all these subsequent moves? So you drill down deeper and deeper recursively until you get to the base case. And the base case would probably be a counter of some sort where you say, okay, I will drill down to 8 moves. And so the counter goes down to 0. And then at that point, you have to evaluate how good is the position of the player at that point. So you evaluate it and you return a value. And then you compare that value with another position that was analyzed. And then you return the position associated with the larger value. And so you return all the way back until you get to your first move. And then the returned value that's the greatest is associated with the best move. So there you go. There's a recursive chess program in 2 minutes. Yay. Okay. Data structure examples. Okay, these are the ones that are more important for this class. You can use recursion when you're analyzing various data structures. We'll talk about trees towards the end of the semester and also graphs at the very end of the semester. And the methods that you'll use to traverse the trees and the graphs and to analyze the trees and the graphs. Those methods, they're going to be much easier if you use recursion. And so, yeah, we'll use recursion for those. So use recursion if you have a problem that has a natural recursive solution, but the solution, it can't be too dependent on speed because recursive solutions tend to be slow. So my guess is that with the chess programs, they probably don't use recursion because it would get pretty slow. You need to be fast because you got humans who want the answers quickly. Anyway, if speed is critical, well, sometimes the recursive solutions are just too slow. So then you need to implement them with loops, okay? And so why are recursive implementations slow? I ask rhetorically because the answer is right there. Recursion uses lots of method calls. That's the whole point of recursion. You get a recursive method call. And then it calls a method, and it calls a method. Each time you call a method, it slows things down because method calls have lots of overhead. The overhead, that's the things that you got to do every time, regardless of the algorithm that you're working on. So every time you have a method call, you've got to save all of your local variables, and then you've got to go find where the method is in memory. And then when you get to that method, you've got to assign all of the arguments to the parameters. And then you got to allocate space for all the local variables in that method. And then when you're all done, you got to return to where you were originally. So all that's overhead and it slows things down. Any questions on this slide? Okay. Next slide. Converting, oh, I need to mark Mel as asking a question or answering a question. Probably both. Has Rolf joined us yet, or Levi, or Ozoda? Ozoda is here. I thought I heard Ozoda.
Yes.
I'm
here. My practice got out late.
Okay, Levi is there. Oh, Levi, are you in the car?
Yeah, I'm on my.
You're on your motorcycle this time?
No, I'm not on a motorcycle.
Okay, good. That's good. No
I'm just playing
Rolf.
class to the speakers in my car.
Okay, good. Good. And then Ozoda, no video this time either? You're on mute there, Ozoda. Can't hear you.
I'm saying I'm here.
Oh, there she is. Yay. Okay, we got video Ozoda. Very good. Okay, next slide. Converting recursion to iteration. So yeah, sometimes you don't want recursion because it's too slow. So in that case, you might want to implement your solution recursively first because it's easier. And then to improve efficiency, you convert it to an iterative solution. So let's talk about that a little bit. Okay. Now, sometimes it's not worth it to convert to iteration because the recursive implementation is so much more elegant and it's reasonably fast. But yeah, sometimes you want to do it, even though you will want to convert to an iterative solution, even though it's a bit of a pain. Now, when you do the conversion from recursion to iteration, it's going to be easier if the recursive solution uses tail recursion instead of other recursions. So tail recursion is when the method's recursive call is the last thing that's done in the method before returning from the method. Okay, it's the last thing that's done. It doesn't have to be physically the last piece of code in the method. No. It's the last thing that's executed before the return takes place. Okay? So it's all about what happens at the very end when you're executing. There are no additional operations to execute. That's tail recursion. It's called tail because tail means something at the end. Stop me if you have questions and earn your attendance point. So here's our original factorial implementation. This is probably the most straightforward implementation. This is what we did. I am maybe on Thursday or Tuesday of last week. I'm not sure. Probably Thursday. Okay, that's straightforward. At least I think it's straightforward. I think it's the most straightforward solution. So if you're down at 0, then you return 1. That's the base case. Otherwise, you return n times this recursive method call. Okay, that works great. It's very elegant. But suppose you want to convert this to an iterative solution. Then the first step is to convert this to a tail recursion version. So how can we do that? Any suggestions? Well, as a hint, I've told you the method call right there. Okay, yeah, you're going to need some hints for this. This is your first tail recursion conversion problem. So one hint is that this is the method call. So we've got 2 arguments. Okay, that means we're going to have 2 parameters, right? So public static int. So far, that's the same as above, factorial. And the first argument, or the first parameter, I should say, is the same as before. It'll be int n, comma. Now the next parameter will be, it's pretty standard for tail recursion, although it's not an absolute rule. But we're going to pass in as the second thing, the second argument that's passed in will be the result that you're looking for. And so then we can return the result later on. So I'll call that int result, like that. So initially, we're passing in a 1. So we haven't gotten very far. When you call the method recursively multiple times, this result will improve. But initially, the result is 1. That's our starting point, 1, okay? And that should make sense. If you're calculating the factorial the way you would without recursion, you'd start with 1. You'd say 1 times 2 times 3 times 4 to get the factorial of 4, right? Okay. So this is our initial result. It's our starting point. So you pass the 1 in. The base case. Okay, the base case will be pretty much the same as before. The if heading will be identical. If n equals 0. So here's the case where I am violating my rule about curly braces. And I'll do that quite a bit this semester. And I think I mentioned that previously. One reason that I'm omitting the curly braces sometimes this semester is because you guys are more advanced students. And so you should be comfortable with the idea of allowing one statement with the risk that someone else later adds a second statement, and then you'd have to insert the curly braces, right? Also, I'm doing it this semester because sometimes I've got a lot of code that I want to stick in the slide, and it just saves space. So I'm going to omit the curly braces this time. On your homework, I will allow you to omit the curly braces, but don't just do it all the time because you can. Do it if it looks good, okay? In this case, it's a very small if statement. No one's going to get confused if you omit the curly braces. Okay, so we have if n equals 0. And we're not going to return 1 here.
And we return the result.
Yeah, that's right. Yeah. We want to return the result. Wow. Well, now that was very impressive. Holy cow.
I was shocked myself.
Man, oh man. Yeah, and that's not provided in the printed slides. So she just got that out of her brain. I forgot whether the book has this exact answer, but even if so, you're probably not looking at the book and you read it and you remembered it, or just you dreamed it up. I am very impressed. Okay. Attendance for Ozoda. Okay, Ozoda, you can go to sleep now if you want. But I hope you don't.
Bye.
No, don't say bye.
I was just kidding, John.
Oh, good. Okay, good. Okay, so then, man, I can't spell else today. Okay, so there's our base case. It's still nice and clean. All right, so you drill down until you get to the base case, and then you're done. Because the goal here is to change the value of result. Each time you pass it in, it's improved. It holds the result. Okay, so the else will have a return. Return what? Okay, this is not easy. This is like one of the homework questions.
Is it also a result?
Okay, so we could say result there. Or maybe something.
Result equal to
Who's that? Is that Ralph?
yes.
Okay.
I think it's gonna be result equal to n and then factorial n minus 1
And
multiple factorial,
multiply.
yeah, multiply factorial n minus 1.
Okay. So yeah, that's reasonable. And this is the most straightforward solution, okay? But it doesn't solve the problem in that the recursive method call is not the last thing that's executed. So it looks a little bit different than this. It's got the assignment statement, and we're using result, and that's good. You do want to update the result here. But it still violates that rule that I said, okay, with tail recursion, the very last thing that's executed has to be the recursive method call. Notice that the recursive method call is at the right of this asterisk. So after this recursive method call finishes, then the result is applied to this multiplication operator. So the last thing in this method is not the recursive method call, it's multiplication and then actually assignment. Okay, but Rolf has the right idea here. We want to update the result so that it's in, okay. Any other suggestions? We want to update the second argument when we call the factorial method. So here's our factorial method call, okay? So what are the two arguments that go in there? The first argument, can someone give me the first argument?
Do you want n minus 1?
Yeah, good. Let's see, who said that?
Peter.
Peter, okay. Let's see, I shouldn't have to ask. I'll put the speaker as my only video in my first computer. So now it should be obvious. Yeah, Peter is up there. I've got my gallery view on my other computer. Okay, so Peter says n minus 1 right here as the first term. Yeah, that's correct. Okay, and so that's the same as before. So the only difference, well, there's a few differences. So we've got a second argument. And what is the second argument?
Would it be
It's just in.
Now, Levi came up. So
Yeah.
maybe it's Levi talking. Okay, go ahead.
Is it just like n to n? Or just n?
N, okay. N. Yeah, we're going to use n. Good. Okay. There's a little bit more you have to do with n.
would it be times result or something?
Yeah, that's it.
Okay.
Okay, there's your answer. That's your final answer. This is recursion. So the final answer, some of you guys are probably a little uncomfortable with. Got to have faith. Now, when I said that, when I taught this course a year ago, I had a student who he would start playing the George Michael song, "Got to Have Faith." Anybody remember that song from 15 years ago? No? Nobody remembers? Jessica, no? Oh, man. Okay. Well, my student and me are a little bit older than any of you guys. So, yeah. I should have had that song. Maybe I'll get it for next time. Okay. So there you go. Now I say you got to have faith. That's part of it. But also it's reasonable to spend some time thinking and talking. So, okay. So you got to create the result, right? Okay. How do you get the result? Well, we passed in the partial result. Like the first time we passed in a 1, right? So the first time this method is called, that's a 1. And n would be what? The first time this is called, what is n?
5.
5, right? So it's going to be a 5 times a 1. Okay, so it's a 5. Okay, let's trace it. So you pass in a 5 for your result. Is 5 equal to 0? No. So down here, you've got a recursive method call. So you're passing in a 4 right there. Okay. Oh man, is there a mistake? Holy cow. I bet I explained it wrong. Maybe there's a mistake. That's in a 5. That'd be a 4. Oh, okay, I didn't trace it correctly. Okay, let me go back. This is in main, okay? So you pass in a 5 and a 1. So n is a 5. No. 5 times the result. So that'll be a 5. That's a 5. Oh, and the n is a 4. Okay. Okay, let me start. I actually, yeah, I made one mistake. Let me start from the beginning though. Okay, and I'll try to go slowly so I don't confuse you and me. So we're passing in a 5 and a 1. That's a 5 and that's a 1. So here's our recursive method call. And I think we can agree that the first argument would be a 4, right? N minus 1 is a 4. And then the result here would be n, which is a 5. 5 times 1 is 5. So the second time this method is called, this is a 5 and this is a 4. Right? Nobody is nodding affirmatively. Oh man, should I start over? You know what? I'm going to take advantage of my poll. Yes, might be the only time I do it. So before the semester began, I was trying to get anonymous polls. So we're going to do that. Launch polling. Okay, now on your screen, did you just see a question come up? Do you understand what was just covered? Well, nobody's even saying yes for that.
Yeah, I can see the poll.
Okay, thank you,
I
Peter.
answered it.
Okay, So yeah, don't tell me, no, don't tell me what you say. This is supposed to be anonymous. This is better than face-to-face, because I do this all the time face-to-face, but then it's not anonymous. So go ahead and answer this. You know, tell me whether you understood the trace so far. Okay, I've only got, oh, I got 2 people saying yes. 2 people saying yes.
It went away for me. Yeah, mine went away.
Wow, that's pretty harsh. Sorry about that. Huh. Too slow. Wait, what's that expression? Gosh, my kids had this game. Too slow, up high, whatever. You know what I'm talking about? Where you do the high five.
Down low, too slow. Is
Down
that what
low,
you're
too
talking
slow.
about?
There you go. Yeah. Down low, too slow. Anyway, so I see 2 people say yes, 2 people say partially, and then the others, I don't know if they know or not. Okay, I'll try it one more time and then we'll move on. So you pass in the 5 and the 1, okay? So n is 5, which is old as 1. And then down here, you're calling it recursively. N minus 1, that'd be a 4. N times the result. Okay, that's a 5 times 1, because the second argument was a 1, right? So the second time this method is called, you're passing in a 4 and a 5. That's where I stopped before. I'm going to continue now. Okay, that's a 4. Is 4 equal to 0? No. So you go down here. So we're going to call the method recursively with 4 minus 1. That's a 3. The result was a what? It was a 5, because we had a 5 times 1. You could do this on paper, and maybe next time I will do it on paper. But this time I'm trying to just talk it out. So it's a 5 times 1. Okay, so down here, the n was a 4. So it's a 4 times 5. That's good. To calculate the factorial, it's a 5 times 4 times 3 times 2 times 1. That's how we will do it. Go ahead, Cheyenne.
So where is n like actually changed?
Here.
So that updates.
Yeah. The parameter is called n. It's equivalent to saying n is assigned n minus 1.
Oh, okay. I got it now. Okay.
And what you just asked and what I just answered is the magic of converting this to an iterative solution. You recognize that this is an assignment. We're passing in n minus 1. It gets assigned into n. So it's equivalent to saying n is assigned n minus 1 with an iterative looping solution. But yeah, that's what happens. Okay. Anyway, if you want me to trace this fully, stick around after class. Okay. And that's how it works. I encourage everyone to trace some of these recursive solutions on your own. I started it, and I'll let you guys finish it. And if you want me to finish it with you, we can do that after class. But eventually, you're going to need to get to the point where you don't have to trace all of them. But it's good to trace a few simple ones to get comfortable. Okay, so there's our tail recursion version. Any questions? I'm going to shut down my poll. Okay, there's my cool innovation. Man, so many innovations with Zoom and polling, and wow. Hope I get credit for all this. Probably not. Oh, well. Okay, so continuing on, we're trying to convert recursion to iteration. So we're going to use tail recursion as the starting point for this little algorithm here, okay? So the previous slide talked about how you convert it to tail recursion. Yeah. These are not hard and fast rules, by the way. I just had an example, and it kind of worked with tail recursion. It's not always going to be easy. I don't have rules for how you do it. You just kind of have to think. Okay. This is my attempt at having an algorithm where we convert tail recursion to an iterative solution, but it's not a hard and fast algorithm. It's a rough. You'll see on the next slide when we do the example that when we convert our factorial tail recursion solution to an iterative factorial solution, we will follow this algorithm pretty closely. So that's good. Okay, so step one, replace the base case if statement with a while loop that uses a negated version of the if statement stopping condition. That'll make more sense when we look at the example. Within the loop, we're going to add an assignment statement for each of the method's parameters such that the parameter variable gets assigned the value in the recursive call's associated argument. Okay, there's a lot of confusing words here, I think. When we look at the example, hopefully this will make more sense. Basically, we're going to do what we talked about in the previous slide. We'll do an assignment for the parameter or parameters. After the loop, we're going to return the variable that holds the incrementally built value. So remember in the previous example, we had a result variable. Yeah, we're going to return the result variable. Okay, so that's the idea. Feel free to ask questions now. I realize it's probably hard because these are just words that might not make a whole lot of sense at this point, but hopefully they'll make more sense after we go through the example. So here's our tail recursive solution once again. So now let's provide an iterative version of the factorial method. So public static int factorial int n. Okay. Now I have n right there instead of two parameters. Previously I had n and result. That's not in my steps over here, how many parameters there are. I'm pretty sure it'd be impossible to have an algorithm that worked all the time. This is going to work for this particular example. We don't pass in the result as an argument / parameter because we're going to implement a result variable. I should say we're going to declare a result variable as a local variable. We'll assign it within the method. We're not going to call the method recursively, so there's no need to have a result parameter. Okay, we're going to assign the result in here as opposed to assigning it as a recursive method call argument to parameter assignment. Anyway, no parameter for result. Like I said, we're going to have a local variable named result. And what do you want to initialize it to? Who wants to answer a question who's not? Let's see, Levi has talked. Zoda has talked. Ryan has talked. Jessica and Cheyenne, have you guys spoken yet?
I answered one question.
Oh, Cheyenne asked a question, is that right? So that counts. And Jessica, you did something?
I answered one question.
Oh, whoa, okay. Better than Cheyenne then, huh? Yeah, one-upping the Cheyenne. Huh. No, Cheyenne, it was a very good question. You get maximum credit for that question. Yeah, because it sparked our conversation about the assignment. So that gets double credit there. Yeah, double credit means nothing, of course. Okay, so let's do this. End result. What does result get initialized to? Nobody needs the credit. Now it's just because you're a good citizen. No, Mel's
Probably
not a
one,
good
yeah.
citizen. Not a good citizen, Mel.
Citizen now.
Who spoke up? Levi. What do you want to initialize it to?
I didn't speak, but
Yeah.
I just unmuted myself for a second.
Oh,
It was
Peter.
I think.
Go ahead, Peter.
I said one.
Yeah, one is great. Okay. Yeah, we're trying to find the factorial. Okay. You could initialize it to n, which is kind of what we did with the recursive solution. But it's going to be a little bit easier if you start with one. You can do it either way, though. Okay, we're going to start with one. Okay, now on the previous slide, I said we are going to replace the base case if statement with a while loop such that the condition is the negation of the base case if condition. So the base case if condition checks to see if n equals 0. Well, we don't want to check to see if it's equal to 0. We want to check to see if it's greater than 0. While n is greater than 0. And you could say while n is not equal to 0, I guess that would be a more formal negation of this condition, but I think this makes more sense. While n is greater than 0. Okay, so on the previous slide, we did the first bullet right there. Within the loop, add an assignment statement for each of the recursive method's parameters. You know, I need to change that because no, oh yeah, we do. We do it for both of the parameters. That's true. Okay, so we've got 2 assignments for these 2 parameters. Okay. I'm going to start with result. And there's a reason for that, which we'll get back to. So result is assigned what? Okay, we're going to do the assignment like this. Okay. Now this is a factorial method, and so it's easier to do the factorial method with just a loop in the first place. I get it. You know, so we're making it harder than it needs to be. But I want to give you an example so you can apply this to your homework, and you can apply it if you have some sort of issue in the real world where you need to convert a recursive method to an iterative method. So our algorithm on the previous slide said we're going to have an assignment for each of the parameters. So the result parameter is going to be assigned to what? This is what Cheyenne and I were talking about previously, right? It's assigned to what? Notice the cursor circling.
N times result.
Hey, look at that. Ozota comes through again. Woohoo!
It was Cheyenne, it wasn't me.
Oh, man. Darn it. I'm really dissing Cheyenne today. Sorry about that, Cheyenne. Man, you deserve more credit. Huh. Where's your dog today?
I can get my dog if you want to see her today.
I probably need the dog. I'm being mean to you today, and I shouldn't be mean. I'm kidding. You don't have to get your dog. The dog is probably preoccupied with more important things. Okay. So we do the assignment here. Thank you, Cheyenne. Okay. Now better style says what? I started the bad style, by the way. Instead of the normal assignment operator, what should we use here?
Times equals.
There you go. Yeah. Mel is the style guru.
I don't know about that.
Mel
Apparently,
is very
my dog.
meticulous.
No, apparently my dog is the style guru.
Oh, good. The dog is the style guru.
He gets very jealous when I talk to my computer.
Uh-oh. Bad news. What's your dog's name?
Finley. He's been behind me, but he just recently got down.
Finley or Henley?
Finley.
Finley. Cool name.
Yeah.
All right.
Thanks.
I wish my name was Finley. Okay. So we did result times equals n. That's our assignment for the result. And then what about the assignment for the n? What do I do there? N is assigned n minus 1, right? It's the same deal. The argument was n minus 1. It's assigned into the parameter, so we're implementing that same logic. So n is assigned n minus 1. Okay, Finley, do you have any objections to that statement there? Style guru Finley? Uh-oh. Finley ate Mel. Darn it. Oh, there's Mel. Okay, good. There's Mel. Whew. I asked Finley a question, Mel.
Do you hear the sirens?
Yes, I do.
Yeah,
Oh,
he's a
more
firehouse.
interesting
He's a firehouse dog, so he really likes the sirens.
Of course. Okay. Other than that, I'm sure he would be much more interested in data structures.
Oh, yes, that's actually what he listens to when I leave.
Okay. Okay, so no, we don't want n is assigned n minus 1. Finley suggests what for better style?
What's the operation? Plus? Or minus, yeah.
There you go. Very good. Okay. Okay, so we did the 2 assignments. Now, you might have wanted to do the n first, because n is the first parameter up there. Why would that be bad? Anybody? We'd have incorrect code if I did n first.
If you did what?
If I had this statement above this statement, if I moved it, if I moved that up, I can't move it, darn it. You guys know what I'm talking
Because
about? Moving
you
this
mean
up?
move it above the result or move it above the while? Yeah. Well, then your result would not be correct.
That's right, because we'd be using the wrong n value.
Well, yeah, it'd be
Okay.
decrementing n.
Yeah, you
That's a
decrement
word, right? Decrementing.
Yeah. We'd be decrementing n first. You don't want to decrement n first and use that new value of n. No, you want to use the original value of n. So you need to keep it the way it was. Gosh darn it, now I can't undo that. Control Z doesn't work in this box. Ah, the shame. Okay, there you go. So there's our loop. We implemented the first 2 steps on the previous slide. And then after the loop, you want to do what? Step 3, return the variable that holds the incrementally built value. So that means return result. There you go. Got it? Oh, good. There's Kyoto, Cheyenne's dog. Okay.
Keela.
Oh, darn it. I was close. Keela. Is it Keela? Wait, there's 2.
There's Alaska.
You cloned your dog. Oh, that is so cool. Alrighty, Alaska and Keela. Okay. Okay, that was a prerequisite for this class, by the way, is having a dog. Levi?
Do I fail now?
I have I have a golden doodle and a royal poodle at home.
Okay, that's good enough. Everybody else has got the prerequisite. Jessica, you got the prerequisite dog too? Okay, good
I
deal.
do. I have 2 dogs.
2 dogs, okay. I'm not going to check with everyone else, but I can trust that you looked at the syllabus. Okay, so we're still talking about converting recursion to iteration. So we talked about how to do it manually. Now, I'm not saying it's easy. I'm not even saying you can do it all the time. No. But yeah, sometimes you can do it. Now, compilers will sometimes do this for you. And it's not easy for them to do it, but they get paid a lot of the compiler software programmers. They probably get a lot of money, the people at Microsoft and people at Oracle. Anyway, some compilers will sometimes automatically convert tail recursion methods so that they are iterative. And they'll do that behind the scenes. So as the programmer, you don't even see that's going on, but you can just check an option and says, yeah, I want to do that optimization feature. Now I've learned that happens more often for functional programming languages and low-level system programming languages. Last time I checked, I did not see it for Java. Anyway, low-level system programming languages and functional programming languages, it's easier because functional programming, and more important, because they have a lot of recursion there. Functional languages are languages where there are no side effects for methods. I'm not sure if you guys understand what that means. Side effect means that something happens in the method other than just returning a value. Something happens in the method that affects the rest of the program other than just returning a value. That's not allowed for functional programming languages. Functional programming languages, every method only affects the rest of the program in one way, and that is returning a value from a function call or from a method call. Anyway, those languages lend themselves well to this optimization. And low-level system programming languages like C, that's where speed is very important, so optimization is very important. Anyway, just realize that some languages have that optimization feature. And we're not going to use it, but just be aware of that. Okay, another concept here related to recursion. Different types of recursion. There's direct recursion, and that's what a method. Oh, I'm sorry, I didn't give anybody an opportunity to ask questions. Any questions? It's just a concept. I don't know if I gave people enough opportunity to ask questions here. This stuff is hard, so I want to go slow. But if you're getting it and you're bored, and then okay, we'll move on. Okay. So either you're getting it or you're bored. Okay. Either one's good. Different types of recursion. There's direct recursion. That's when a method calls itself, and that's all we've been exposed to so far. When most people think of recursion, they think of direct recursion. So when a method calls itself, and then there's two forms of direct recursion. You can have single recursion, and that's where in the method, there's only one recursive method call. There's also multiple recursion, and that's where within the method, you have multiple recursive method calls to that same method. So you remember an example where we had single recursion? We just did it. What was the method where we had single recursion? That's where there's one recursive method call in the method.
Factorial one?
Hey, Cheyenne. That's right, factorial. Okay, how about an example where we had multiple recursion? Let's see. Oh, yeah, I can remember now. Let's see, is there another one? No, you guys don't remember from last lecture? Towers of Hanoi. Towers of Hanoi, we had a recursive method call for the subset of disks, and then we had a print statement, and then we had another recursive method call for that subset of disks. We moved it to the target tower at that point. There's also indirect recursion. It's also known as mutual recursion. That's where you've got two methods that interact recursively. So one method calls the other method, and then that second method calls the first method, and then they go back and forth, back and forth. It's indirect recursion. It's not as common, but yeah, you'll see that every now and then, and we'll see it on the next slide. This one's pretty cool. Not terribly efficient, oh well. A part of the data structures class is not just learning material because data structures are used in the real world and it makes you more marketable. Part of the data structures class is because this is a computer science degree, and if you go to graduate school, you're going to need to know some of these cool concepts that aren't used all that much in the real world. But yeah, you want to get the master's degree because you want to feel good about yourself and brag and whatever, and maybe get paid $5 more. Oh well, I'm kidding. It is worthwhile. I mean, I've got a master's and it wasn't worthless. I got paid a little bit more. It's a little bit easier to get a job. So anyway, here's a cute little example that uses mutual recursion. Okay, so this code figures out if a passed in value is even or odd. Okay. Now, it's much easier to figure this out without mutual recursion, but okay. Here's an example. It's kind of hard to come up with a small mutual recursion example, but yeah, this is that. So, does anyone want to try to explain how this is even method works? Or do you want me to explain? I'm the teacher. I get paid for it. Anyone want to explain it for me so I can give my throat a rest? My voice a rest? No? Okay. Okay, so you pass in the number and you check the base case. If the number is 0, 0 is an even number, right? So you return true. Okay, base case, pretty straightforward. The else, it's a little tricky. Okay, so if it's not the base case, if you're not at 0, then you call the other recursive method. You call isOdd. You call that other method. It's embedded inside a return statement. So we're calling isOdd, and then we pass in a value which is smaller than the original value. And that's a hallmark of recursive method calls, is you're going to need to pass in an argument which is smaller than the original parameter. If you don't do that, then you're never going to get down to the base case. You'll have an infinite loop. So we pass in a smaller value. We pass in num minus 1. Now, it's not exactly num minus 1. It's the absolute value of num minus 1. Why do I need the absolute value of num minus 1?
So you don't keep going back?
Yeah, that's right. You don't want to have an infinite loop. You want to hit the base case. If you start with a negative number, you'll go further negative each time you call this method. And so you'll never get to 0. Got it? Now, it might seem a little bit weird to change a negative to a positive, and yet it's still going to work. But think about it. An even number, -3, okay. It doesn't matter. The sign doesn't matter when you're determining whether it's even or odd. A -3 is odd, a +3 is odd. A -5 is odd, a +5 is odd. -6 is even. Got it? The sign doesn't matter. So to avoid an infinite loop, to cause us to eventually get to the base case of 0, we're going to apply math.abs. Okay? So there you go. So we call isOdd. We pass in 1 less for our num value. And so we go over here and we do what? Okay, get out a piece of paper and try to write down the code for that. We've got about 10 more minutes of class. We might be done early, but yeah, seriously, get out a piece of paper and see if you can come up with an answer.
Doesn't it end at 5:05?
Oh my goodness. We've only got 2 more minutes then. Oh, darn it.
Just
Oh,
some
well.
seconds, actually.
2 minutes and 2 seconds, actually?
No. It's you have just like under a minute.
3 minutes. Okay, got it. Okay. So
I think your counter is going in the wrong direction.
counter's
You might have
going
a minus
wrong
minus.
direction. Okay. That could be. It could be the old dreaded minus minus. Okay, if num equals 0. Okay, I'm giving you a head start here. Okay, so the base case is the same. What do you want to return?
Oh,
Our isOdd method. Say
it's
that a
gonna
little bit
return
louder.
false.
Yeah, false. Yeah, if it's 0, then it's not odd.
Yeah.
Man. Ozoda's a shining star today. Wait, that wasn't only Ozoda though. Because Peter also. Peter, you're a shining star as well. Everybody's a shining star today. Even the canines. Especially the canines. Okay, so there's our base case. And then else, we're doing mutual recursion. Return is even math.abs. Okay, and then what? It's kind of hard, but if you guess that it's similar to the other one, you'll be guessing correctly. Just num minus 1. Like that. There's your answer. So, the whole point of this was to show an example of mutual recursion. Now, you might feel a little uncomfortable because it's a little confusing, and so it would require you to think about it and trace it. Now, we can trace this verbally next time. Actually, next time, maybe we can trace a little more formally with paper, and I'll draw variables down. I will draw variables if you want, but I encourage you to do it on your own as well. Okay, but I think we're almost out of time. So, any final questions for the group? Okay. Well, as usual, I will turn off the recording and give you an opportunity to ask individual questions if you have any. By the way, you don't need to worry that you're missing out. Usually there's nobody that's interested in talking to me one-on-one. Very
I'm
sad.
interested. I'm interested.
Okay. Okay. So let me turn off the recording here. Bye.